Thanks, everybody. As Ollie said, please interrupt me with questions. I know this is a very sort of mixed audience, so what exactly things are obvious to me and obvious to you is not going to be perfectly aligned, but hopefully you'll get something interesting out of it at the end. So the plan for today is to talk about a problem from combinatorics that turns out to have lots of applications across, hopefully, to things that you all like as physicists. So even if you're not totally inspired by this particular problem, it should be interesting eventually. So the title of this is Classifying Bounded Ratios. And so the combinatorial problem that we're trying to describe started originally with looking at the set of totally positive matrices. And these are very closely related to the positive Grassmannian that we heard a bunch about last week. These are n by n matrices where every k by k minor is positive. So we can have a nice 2 by 2 example. If I have my little matrix A, B, C, D, then the totally positive part is the part where the 1 by 1 minors, i.e. the entries of the matrix A, B, C, D, these are all positive, and there's one 2 by 2 minor, the determinant, AD minus BC, and I'd like this to be positive as well. Nice semi-algebraic set for your algebraic geometers. There's lots of nice things about this. And one of the things that you can ask about this thing is, okay, I have all these minors that are positive. There turn out to be other relations among these minors, other inequalities that we can get. For example, there's one that says that A times D has to be bigger than B times C. This is an easy rearrangement of this determinant thing. I just moved everything over. But this is also, right, this is the product of a 1 by 1 minor, 1 by 1 minors, and this is some inequality among products of minors that's true across every totally positive matrix. Doesn't matter what those entries are. If it's totally positive, I have this idea. And so the big question is, what other inequalities have to hold? And we can do this for bigger matrices, and we can get slightly more interesting inequalities. For example, say I have a nice 3 by 3 matrix, 2 by 2, and one thing that we can see is it turns out if I take I'm going to write delta sub 2 comma 2, that is this entry D, it's the 1 by 1 minor of this thing, and I multiply by the minor 1, 3, 1, 2. So this is going to be the determinant of the first 3 rows and the first 3 columns, i.e. AH minus B. It turns out this is always bigger than the determinant of this first block, AB, AD minus BC, and the entry in the third row, second column, which is H. You can go through, and the claim is if all 1 by 1, 2 by 2, and 3 by 3 minors are positive, so is this thing. For those of you who don't care about totally positive matrices, but like the totally positive Grassmannian, it turns out I can embed this matrix into the Grassmannian. And the way that I'm going to do that is I'm going to add n columns at the beginning. So this is, I'm going to add 0, 0, 1, 0, minus 1, 0. And this makes a nice 3 by 6 matrix. And I'm going to consider the row span of this matrix as a matrix in the Grassmannian. Why did I pick this particular matrix and this particular sign pattern? Is now the Plücker coordinates of this matrix are exactly the same as the minors of this n by n matrix that I have here. So for example, if I take the Plücker coordinate that is the first, third, and fifth column of this matrix, so I'm going to look at this one, and this one, and I take the determinant of these things, the determinant will be exactly this matrix H, and the choice of these rows and this sign pattern makes it so the Plücker coordinate is positive if the minor is positive also. So equivalently to this question about minors, is I could ask on the totally positive Grassmannian, GRKN, let's Grassmannian, what inequalities hold among Plücker coordinates? Yeah, I can definitely do that. So, so we recall the Grassmannian, GRKN. This is the set of k-dimensional subspaces. We can decide Rn, Cn. Here I'm talking positivity, so we'll take real numbers because then things are nice that way. This is a projective variety. It embeds in n-choose k-dimensional projective space via what's called the Plücker embedding. And so given a k-dimensional subspace, I can represent it by a k by n matrix with columns v1 up to vn. Given I equals, pick some indexing set of k numbers between 1 and n. Then I get a function pi, which goes from the Grassmannian R, that's given by pi of some equivalence class. I take my row span in my matrix that represents some k-dimensional subspace, and I'm going to take the determinant of the k by k matrix that is columns v1 up to vik. And it turns out that if I take a different representative of this matrix, I can change my basis. That will correspond to multiplying this matrix on the left by some k by k matrix A. And the determinant is multiplicative, so I will get pi of am is the determinant of AV1 up to AVI1 up to AVIK, which is the determinant of A times the determinant of VI1 up to VIK. So every Plücker coordinate changes by this determinant, and so I can say that this is a projective, this list of all of the Plücker coordinates is well defined up to simultaneously scaling, and so this is a projective variety. I'm often not going to worry so much about the projectiveness of this and just treat the coordinates as the affine cone of this Grassmannian. I'm not an algebraic geometer, so I'm happy to do that. Hopefully that won't be confusing when it happens. Yeah, so these are the Plücker coordinates. They're the nice natural coordinates on the Grassmannian. And the totally positive part, GRKN greater than 0, is the subset where all the PI are positive. So, okay, so we have this nice semi-algebraic set. We have this nice thing. It shows up in physics and your amplitude calculations. These Plücker coordinates show up in various things. Yeah. Yeah. Yeah, so this sort of goes with this embedding that I had here. it turns out all the maximal minors of this Grassmannian correspond to all of the different minors of this matrix. Basically, in this embedding that I've picked, how many indices are in the first n things is the complementary size of my minor. So by taking all the maximal minors, by changing how much I pick in the beginning, I get all of the different things. So it really is, it's really an equivalent problem. This one only ends up in sort of the middle Grassmannians, the GRK, 2K Grassmannians, because I take my K by K matrix and extend it out this way. Still an interesting question for general K and N. And it turns out that these middle Grassmannians get complicated much more quickly than if I fix K and take N bigger. So it will be nice to have some more examples. Yeah. Yeah. I believe the simple answer to your question is I fix my I'm interested in the set where it's cut out by exactly the equations the minors are positive. There, we'll see a little bit later, there's this semi-algebraic set also has the structure of a cluster variety. And so I can take different generating sets from the cluster algebra, and if only these subsets are positive, it defines the same. I have lots of different sets of generators based on this cluster structure. Question or okay. Yeah, as I said, I'm not an algebraic geometer, so the semi-algebraic set is not. I'm interested in the semi-algebraic structure, but that's not my primary focus. Okay. Other questions before move on? Okay. So the general question of, all right, so I take this matrix, I have these coordinates, and I ask what are all the possible inequalities among polynomials in these coordinates is really hard. I have no idea how to solve that general question. But what we can do is make a simplifying assumption. I'm only going to look at multiplicative inequalities. I want to multiply some Plücker coordinates, I want to multiply some other Plücker coordinates, and I want to know, is one product bigger than the other one? Like these examples that I have here. And so with this simplification, then there is some things that we can say. We're going to focus on multiplicative inequalities. So I'm going to take a product of some things, and I want to know that it's greater than product. And the nice transformation that I'm going to do to get the title of the talk is I'm going to divide through by the left-hand side of this inequality, and I get an inequality that there's some constant bigger than the product of mj's divided by the product of mi's. This is what I will call a bounded ratio. This is some, I take my nice functions that I like, my Plücker coordinates, my minors, I'm going to make a nice ratio of them, and the question is, when is that ratio uniformly bounded on the whole set of positive elements? Looking ratios, uniform bound. Why are we interested in this sort of thing? It's an interesting combinatorial question. From these inequalities, I get other functions that are positive on the positive Grassmannian, on the totally positive matrices. These maybe had some relations to trying to find semi-canonical bases of things, but also I'm a mathematician. This is a nice set. It turns out there's a nice classifying answer for this. So a brief summary of some early results. So S. Follett Gekhtman, Johnson in 2003 classified products to principal minors. So this was a very restricted subset of this thing. We only looked at the minors that used the same indexing set on the top and the bottom. We multiplied exactly 2 of them together, and we know what all of those are. This got generalized quickly to non-principal minors. And then a few years later, Bucher and Froh 8 generalized to the totally positive Grassmannian. So this is a nice problem. There are some conjectures about what the bounded ratios will look like, and we'll see which ones of these we can talk to a little bit later. One of them, which is a sort of surprising fact, is that every bounded ratio is bounded by 1. So it turns out if you're uniformly bounded, bound is just by 1. In the inequalities that I showed you before, there was no actual constant in the multiplicative inequality. I didn't need to scale one side. This is really surprising. It will come up a little bit more naturally from how we look at it later. This turns out to definitely, I think, be true. One sort of consequence of this, or a slightly stronger version of this, is that every bounded ratio is, quote, subtraction free. And the idea is if you have some positive parameterization, I can look at q minus p, the denominator minus the numerator, and that this is manifestly a positive polynomial in some parameterization. We'll talk a little bit how to get some of these parameterizations later, but the claim is that there's some way to write all of these minors just as polynomials in some nice initial variables. And one way to see that your ratio is bounded is if the denominator is smaller than the numerator, i.e. the difference is positive across this whole parameterization. And some of these conjectures were verified. In GR24 and then generally in GR2N. And also for GR36. In this, just later on also.
Okay.
Yeah.
Okay.
Yeah. In this case, what they discovered is that this Plücker bounded cone is generated by ratios of this form: I, j plus 1, and then generically some set S, j, I plus 1, and some set S, divided by j, S, two indices I and j. So this is the sort of problem that we'd like to classify. So how do we understand what about I have a bunch of ratios. How could I ever classify what all of them are? So it turns out what this means is that the bounded ratios form a cone. If I multiply two bounded ratios, they're still bounded. And it turns out that this is a polyhedral cone. So set of bounded ratios is a polyhedral cone. And what that means is I have this cone that's cut out by a bunch of hyperplanes. If I know what the vectors that generate this cone are, then I know every ratio is just some product of these ratios. So my problem of classifying all multiplicative inequalities turns into, I want to know what are these generating ratios? What are sort of the smallest bounded ratios? Yeah, Ilya. That is one of the things they will see. They have to be invariant under the torus. If they're not invariant under the torus, I can use the torus action to blow it up. Yeah, so this is the punchline of the talk, is it turns out the generating ratios of the bounded cone are exactly the solutions to the U equations. So yeah, that's where we're going. Which is why I thought this might be interesting for all y'all, is that somehow this abstract combinatorial problem is answered by these binary geometries and positive geometries that have become so exciting in the physics community. Okay, so far I've been talking a lot about Grassmannians and totally positive matrices, but in the introduction I said I'm a cluster algebra person. So how did I end up with this thing? So it turns out that cluster algebras are going to give a even more uniform picture of this problem, both the totally positive matrices and the totally positive Grassmannian have a cluster structure. And what this means is that I don't want to give a full, this is what a cluster algebra is. If you want that later, we can do that later, but that usually takes about an hour. So as a sort of small example, there's a cluster algebra. I'm going to say of type A3. If you know what that means, great. If it's not, don't worry about it. The way a cluster structure works is you get given some combinatorial information, in this case a directed graph, that is just a nice straight line. Associated with this graph are some variables I call A1, A2, A3. These are the cluster variables. And this information prescribes an algebra and a bunch of relations among this algebra by this process of mutation. So for example, I can mutate at this second spot. And in this case, what this does is it's going to produce a new directed graph, in this case, just given by reversing all the arrows. And it's going to leave some of the cluster variables alone, and it's going to produce a new variable, A2 prime, that's related to the old one by a relation of the form A2 times A2 prime is the product of all the variables coming in, which in this case is the empty product 1 times the product of all the variables going out. In this case is A2 and A3. And you get a cluster algebra by performing all these possible mutations. And what does this have to do with this sort of positivity? If my initial cluster variables A1, A2, A3 are positive, we can see the form of the relation is going to give me more positive things. Yes. I deviated from my notes slightly, and yes, thank you. Good catch. And so what it turns out is both on the Grassmannian and for these totally positive matrices, I can find the directed graph where I put these minors on the nodes of this graph, and I can get every other minor by doing this mutation sequence. And so this will give me sort of subsets of the minors that are minimal positivity tests. If I test these minors are positive, every other minor has to be positive because I get them by doing this cluster mutation that keeps everything positive. And yeah. So one thing that we can observe is from these exchange relations, it's really easy to obtain bounded ratios In the cluster variables, the idea is all I'm going to do is I'm going to divide by the left-hand side of this exchange relation, and I get 1 is equal to 1 over a2 prime, a1, a3 over a2 prime, and I know both of these are positive because they're just positive products of cluster variables, and I have a positive sum equal to 1. That means each of them is bounded above by 1. So this gives something about this conjecture that everything is bounded by 1 if these are my generating relations. If the generating rays of my cone come from these sorts of exchange relations, then manifestly everything's bounded above by 1. And that is going to give me that thing. So that's, let's see, where did I want to go? Oh yeah, okay. So you might be naturally asking the question, I was telling you about the Grassmannian, I had Plücker coordinates, and I said, actually, there's this other complicated combinatorial structure that you're supposed to look at instead. Why do I want to make this generalization? Well, it turns out that in the Grassmannians 3.6, 3.7, and 3.8, there are non-Plücker cluster variables. And in the cluster algebra theory, these non-Plücker cluster variables are really important. If I will not show you the nice picture. Yeah. Yeah, this has been for all of these, there is a uniform initial quiver and Plücker coordinates. I can tell you a particular starting quiver for any Grassmannian GRKN, and the cluster algebra for the Grassmannian starts from that quiver by doing all possible mutations. Yeah, exactly. In this case, this turns out, so the classification is GR2n is AN minus 3. GR36 is the cluster algebra D4. 37 is E6. GR38 is E8. And these are all what are called finite cluster algebras. This means that when I do all possible I start somewhere and I start doing mutations, it turns out that this closes back up. I start doing some mutations and I get back to seeds that I got before, and if I do this in all possible ways, I only see finitely many things. All other Grassmannians have infinite cluster structure. And so this is something that you might have observed in physics. When you have things that land in these Grassmannians, things are nice, and as soon as I get to, say, GR48 or GR39, all of a sudden you start seeing your square root symbols, and the symbol alphabet gets really bad, and some of that, to me, comes from the fact that these cluster algebras get worse sort of at that point. They end up being, there's some way to connect some of these things, and this is an interesting question. They end up being, there's the set of affine Dynkin diagrams that are infinite, and then there are some doubly extended Dynkin diagrams, and it turns out 4.8 and 3.9 are that sort of thing, and then they connect to bigger and bigger sort of singularities. Something my collaborator Danny Kaufman likes a lot, and so you should talk to her about that if you want nice sort of Dynkin classification of these things. Yeah. There are, it's nice, it's a little bit more complicated because here my directed graphs are all sort of the same weight. And so in the B and C, I have to, but I can do some sort of folding and I can view all these things that way. Yeah, so it turns out that the really beautiful cluster algebra fact that the finite cluster algebras are exactly classified by the finite Dinkin diagrams. Hence, right, so okay, so okay. So for us mathematicians, I'm going to make this problem really concrete. I'm going to define what I call the ratio space. This is a vector space with a basis vector for each cluster variable. And I'm going to interpret the integer points of this vector space as my ratios. So for example, if I had some basis vector 1, 0, minus 1, 1, and this corresponded to variables a1, a2, a3, a4, then I get a nice ratio here, a1, a4 divided by a3, where I just read off the power, each entry of my vector corresponds to the power of the ratio. And this is a nice thing. Adding vectors is equivalent to multiplying ratios. Now I've taken my sort of problem and I've converted it into a nice linear algebra problem. And so now my set of bounded ratios is going to correspond to a literal, nice vector space code. I just have vectors and I want to know what are the generating vectors in this code. Okay. So as was foreshadowed, the way that we're going to do this is we're going to look in finite cluster algebras, and we're going to look at a nice structure on finite cluster algebras coming from physics. Finite cluster algebras associated called the cluster configuration space. These cluster configuration spaces were defined by Med, E, and Lamb. These are generalizations of what Francis Brown called dihedral coordinates. On M0n, hence the name configuration spaces. We have M0n, the configuration of endpoints on disk, and we're going to have other configuration spaces associated with the other finite cluster algebras. These are some nice algebraic varieties. They're defined by equations form u gamma plus a product of omega not equal to gamma u omega to some pairing. So I have some set of variables indexed by a set, and I'm going to take one of them and I'm going to add some to a product of powers of these other things equal to 1. And what they did in this cluster configuration spaces paper is they showed that there is a nice pairing on omega gamma each cluster algebra. So the solution set is, I'm going to say, high dimensional. You might expect from writing down these equations, I wrote down one equation, I have n variables, and I wrote down one equation, n equations in my n variables. If these were all independent equations, you would expect to just get a scattering of points. But it turns out if you choose these powers carefully, you get a sort of a nice space. For example, in this M0n, which is the type AN configuration space, this function, if each of these gamma and omega represent some cluster variable, this is going to be 1 if these appear together in a seed, 0 otherwise. If I have one directed graph that has these cluster variables associated to it, if they can show up together in a graph, then this function is 0. Ooh, I want it the other way. If they show up together, it is 0. If they can't show up together, it's 1. This is directed graph variables. The well-defined thing in the cluster algebra theory. As I said, you start with one of these objects, you have a bunch of cluster variables. Every time I mutate, I change one of them. And each one of these things is enough to grow the whole cluster algebra, hence the name seed. From any one of these, I do all the mutations and I get this. Yes, exactly. So that is a very good point, and we can take this as an example. If I look in the cluster structure for GR26, which is a type A3, one way to view the seeds of the cluster algebra is I can take a disk with 6 marked points on the boundary, or gone if you're not being fancy, and each cluster coordinate will correspond to an edge of this picture, and each seed corresponds to a triangulation. So for example, triangulation like this, and if I label the vertices of my hexagon, in this case, all of my cluster coordinates are Plücker coordinates, and the Plücker coordinates correspond to the indices on each edge. So this is the Plücker coordinate 2, 6, 2, 5, 4. And I would say that these belong to a seed together because they're all in a triangulation. And so this compatibility of seeds also is if the two arcs cross, they can't belong in a triangulation together. And so 1 if they cross and 0 if they don't. So in this case, we can actually write down a nice one of these U equations as an example here. Say I want to write down the one for U26. What I'm going to get is I'm going to add a U variable for each arc that crosses 2, 6. And that's going to be 1, 5, and 1, 4, and 1, 3. So one of the equations in my U system looks like this. 1, 5, 1, 4. There's going to be a bunch of cyclic rotates of this, and there's going to be sort of one other style. If I start with the long arc in this thing, now there are more crossing things that I could have. 4 arcs here. 6. Equation involving U25, and that will be 1, 3, 1, 4, 3, 6, and 4, 6 are the crossing arcs, and they're all to the first power. Cyclic rotates of this, and this would be my cluster configuration space of type A. So it's going to depend on the cluster algebra, for a finite cluster algebra, there's going to be one for each cluster variable. In this case, for GR2n, I get a cluster variable for each Blücher coordinate, so there's going to be n choose 2 of them. N choose 2 variables and n choose 2 equations. And it turns out in this case, what I'm going to get is I'm going to get a 3-dimensional configuration space instead of just a scattering of points. And that 3 is the 3 in A3, and so that's not a coincidence. Okay. Okay, so one nice thing to discuss is what Ilya mentioned. On each cluster algebra, there's an action of a torus, in this case, an algebraic torus action. And this is going to help sort of cut down the space of ratios that I have to look at. So what do I mean by this? Algebraic torus action, act on the cluster algebra by characters of the torus. If you want to be fancy, if you want to be really concrete about this, what I'm saying is, if I have a complex variable z, I have some function mz that takes some cluster variable a gamma and sends it to z to some power times my a gamma. And the claim is that there is some choice of t gammas such that I can make this work. How does this work? In say C star or R star, if I'm doing real things, I can sort of simultaneously rescale everything by some powers of this thing. And the torus is each C star is an S1, is a circle, and I have a bunch of products of different Z's that I can sort of do together. That's where this name torus is coming from, and it's just acting by different powers of the units of my complex plane. Yeah. So if we look back at our original example, I had A1, A2, A3. What I would like to do is say what power of z should I act on my initial variables, and then have it continue on to all of the other cluster variables by the exchange relations. So it turns out all I need to do is choose powers in one seed that are balanced in the exchange relation. So we had the exchange relation before. We said A2 times A2 prime was 1 plus A1, A3. And for each of these cluster variables, I'm going to pick some power T1, T2, T3. And if I imagine looking at the scaling, what I'm going to get is I'm going to get z to the T2, A2, z to the T2 prime, A2 prime is 1 plus z to the T1, A1, z to the T3, A3, and I just need to make sure that all these powers of T agree in each thing, and it turns out that this will continue throughout the rest of. So, what did I want to say from this? Yeah, okay. The point is, on every cluster algebra, I have this sort of torus action. And it will turn out that it's maybe clear that if I have a ratio, if I check the powers of t that I assign to all the cluster variables in the ratio, this power of t needs to cancel out. They need to be homogeneous degree 0 polynomials for every character of this torus action, because if it isn't, I can take z to either be 2 or a half, depending on if it balances out. Write this down clearly. The claim: bounded ratios are degree 0 for any action. Ratio A1, A2, A3, A4, and I act with this torus. I'm going to get z to the T1, A1, z to the T2, A2. In other words, I get z to T1 plus T2 minus T3 minus T4 times this ratio that I had. And importantly, all of these z times A1, z times A2 is a different point, is a different positive point that's in my cluster algebra. In this, so I have another point, and the ratio is changed by z to this power. So if this was bigger than 0 and this was 2, I can keep making my ratio bigger and bigger and bigger by just taking more and more powers of this torus action. Okay, so this idea led, okay, all right. So we've seen two different things. We have the cluster algebra and we have this configuration space, and we want to know how these things are related to each other. It turns out that the cluster algebra, I guess the cluster variety, so the modulo the torus action is isomorphic to the cluster configuration space. So now I have a very nice connection between this sort of physically motivated U systems and these cluster algebras that were around for other reasons. These things are closely tied together. And this is going to be the thing that lets us prove our big theorem. Yeah. This is not, this is Arkani Hamed and Lamb and yeah. So this is, yeah, this was nice. This was really great. We were studying this problem, and then we said, oh, it turns out we have this nice tool to study this thing. They've already proved all of this. This is great. What they showed is that on this side, I had a U gamma. I have a parameterization of this in terms of these cluster variables. It turns out that there is a particular seed in the finite cluster algebra. I'm going to call a Dynkin seed. These are the ones that look like the Dynkin diagram. It turns out from the finite cluster algebra theory, there's always these seeds. I can find one where the orientation of this directed graph is so that it sources and sinks. So sources sink. Dynkin diagram. And if I look at the cluster variables in this diagram and I take the product of everybody going out and I divide by my cluster variable and the thing that I get by mutating at that seed, these ratios exactly parameterize the U system. So if I take these ratios, they're going to solve that set of equations that I wrote down before. It's not at all clear that they should have some nice solutions, but these ratios are the ones that do it. And then the big theorem that we proved is that these ratios generate cone of bounded ratios. Exactly these parameterizing ratios are the sort of primitive ratios that I need to write down any other ratio. And surprisingly, this theorem is not so hard to prove. There's a little bit of technicalities here. So, all right, so this is for the technical word here, full rank, cluster algebras of finite type. So what does this full rank mean? This has to do with the torus action on this cluster algebra. So I said I needed, given a graph like this, I needed to find vectors where the t's were balanced through all the exchange relations. And one way that I can do that is if I take this directed graph, I can write the associated exchange matrix for this graph. And I have this labeled 1, 2, and 3. And so I'm going to get here a nice 3x3 matrix where I record the signed adjacency of this thing. So let's see, we have 1 is coming in from 2, 2 is going out to 1 and 3 is also coming in from 2. And what I get is I get a character of the torus for each vector in the null space of this matrix. In this case, I have one vector in the null space, say -1, 0, 1. And that was going to give me a scaling that makes all these exchange relations balance out. In this case, we can see, for example, if I take t1 equals 1 and t3 equals -1 and t2 equals 0, in this exchange relation, everything is degree 0. Yeah. So there's a little bit of subtlety here. I need this to be full rank. I need my exchange matrix to be rank, to be as high rank as possible. So with this quiver, as it is, my theorem wouldn't apply. Fortunately, there's a thing in cluster algebra theory that I could do where I can add some variables that I call frozen variables. They're places that I'm not going to mutate. They help control exactly what exchange relation I get. It's part of the prescription of the cluster algebra. So the Grassmannian cluster algebra, for example, has some prescribed frozen variables. In GR2N, those are the variables associated to the boundary of the polygon. Those are in every possible triangulation. I can't mutate there or flip there. And the condition of being full rank in this case is that this sort of extended exchange matrix with these frozen variables will have null space dimension exactly equal to the number of frozen variables. So what I have is full rank if and only if the dimension of the null space exchange matrix equal to the number of frozen. I can always add frozen variables to my cluster algebra to make it full rank, so this does apply to every finite cluster algebra with enough frozen variables attached. And so with the sort of last chunk of time, I'm going to give you just a, well, I started a little bit, is giving you some idea of how the proof of this theorem goes. How are these things related to each other? And we use the finite cluster algebra in a couple of ways to make this go. So the first way is for a finite cluster algebra, ratio space B that we talked about earlier, this vector space associated to my ratios, is finite dimensional. I have finitely many cluster variables. And in fact, its dimension is the number of sort of mutable variables plus the number of frozen variables. And so when I'm in full rank case, We said the torus is this dimension of the null space, dimensional, right? I get one torus action for each vector in the null space, and that this is equal to the number of frozen variables. So the subspace of rank 0 ratios is number of mutable variables dimensional. I have, for each one of these torus vectors, I get one independent linear equation for each dimension of the null space, and so it just cuts it right down. And lo and behold, this is also the number of u variables. And so what it turns out is that these u variables are actually a basis for the rank 0 subspace of the ratio space. I have one vector for each thing, so all that I need to do is I need to prove that each u variable parameterization is independent. And then that tells me that every ratio that could possibly be bounded, right, that isn't trivially unbounded with this torus action, is some product of u variables. And if any of these u variables have a negative power, I can prove that the ratio is unbounded. So what I have left is just positive linear combinations of my u variables. In other words, this solves the problem. So this last piece, independence and cone generation, come from finding a path in the variety, sending, say, a particular u gamma to 0, and keeping all other u omegas strictly positive. And this sort of thing is something that you would really like from the way this binary geometry, these configuration spaces show up in physics, right? You like these spaces, I'm told, because when I set one u variable to 0, it makes another bunch of u variables 1, and the configuration space sort of breaks as a product. And this mirrors the sort of recursion and amplitudes that you want to get as you go to sort of different degenerations of the amplitudes. What was not proved in the original paper was that this boundary is actually realizable by a path in the variety. You can just set a u variable to 0 and you sort of see it at the edge, but you don't know that that actually lives at the boundary. So we showed that when your cluster algebra is full rank, you have an actual parameterization in the cluster variables that does this. And the fact that I can do sort of exactly one at a time tells me that they're all independent vectors. If they were dependent, then I would have to send some of them to 0 depending. And if I have a negative power and I send it to 0, that's going to blow up to infinity. So that is a little bit of a rushed hand-wavy connection here, but I want to spend the last couple minutes with some questions that hopefully some of you all can help me answer. And give you some things to come talk to me later about. So okay, so what I've hand-waved at you all at is that we know this answer for every finite cluster algebra. But finite cluster algebras are a small subset of all the cluster algebras that could be. In fact, we talked about for cluster algebras, even just coming from the Grassmannian, I can write down all the finite ones very quickly, and there are many, many other Grassmannians. especially Grassmannians of the form 4 comma n, which is where your momentum twistors are supposed to live, that this tells you nothing about. In fact, in GR48, yeah, I mean, it's just a mess. There are some slightly easier infinite cluster algebras to look at. There are what are called affine cluster algebras, which are sort of only lightly infinite and kind of nice. And so it's possible that this is a really good starting place to generalize. And my understanding is that in physics, one way to look at these is I can look at the cluster algebras associated to surfaces with more topology, say an annulus or a disk with multiple punctures, sort of more complicated surfaces. These are going to give you infinite cluster algebras because there are now infinitely many arcs on the surface. I have the mapping class group action. And so my understanding is that there's been some study of these, in trace phi cubed theory, there's cluster algebras of surfaces involved, and how exactly these things are connected could, studying these configuration spaces could tell you more about this problem of classifying bounded ratios in bigger sets and bigger Grassmannians. I think this would be a nice place to start. Let's see, what other questions do I have? Oh, right. So one thing that I wanted to point out here, and then we'll open up for other questions. In GR36, this gives a, we have a symmetric description of the cone of boundary ratios in all the cluster variables. But the original question was just about Plücker variables, right? These other cluster variables are sort of mysterious. There's some high degree polynomials in the Plücker coordinates, and I need them to have a nice symmetric description, but the Plücker variables is a nice finite set. In GR48, again, the Plücker variables finite, not cluster symmetric. So I have this finite set, but the cluster algebra doesn't distinguish between the Plücker variables and the non-Plücker variables. And that's part of why the cluster algebra is infinite, even though there's finitely many Plücker variables. And so there could be some interesting questions on how do I take this cone that uses all the cluster variables and reduce it down to maybe a smaller subset of only the variables that are somehow physically meaningful or that you care about. In GR48, it turns out that you can, with a computer, you can work out this Plücker bounded cone. The bounding hyperplanes correspond to rays in the tropical Grassmannian, and you get some ratios that are products of 20 Plücker variables divided by some other 20 Plücker variables that are the generating vectors of the Plücker bounded cone. But there should be, in all these other finite cases, adding in these other cluster variables got you something nice and symmetric. So either identifying some sort of physically meaningful subset of cluster variables might give you a nice, more symmetric set of coordinates to look at bounded ratios on that might help shed some light on what on earth these horrible products of Plücker variables are. So in summary, the cone of bounded ratios is given by this cluster configuration space, these U equations that y'all have. And so anything that y'all know about other U equations, other U systems, I think would be very interesting and maybe have some applications across some other positivity. So that's all that I've got for y'all. Thanks. If you got other questions, come find me or